Just a reminder about test 3 on chapter 3. Okay. So on that note, do you have any questions about, you want me to go over any examples of problems or anything? I'm repeatedly asking you this because usually I get to give 2 quizzes and then the test during a typical semester on Laplace transform, so students get a chance to make some mistakes, and then this is a one chance thing, so that's why just want to make sure that all of you are ready for this. Any questions? Any examples that we did in class or in your homework which looked unusual or weird, or or I could kind of give you some time at the end of the lecture to ask if I suddenly put you in a spot. Okay, so think over it, and while I just do a little bit of chapter 4, so I'll teach for maybe 25-30 minutes and then I'll stop. Okay. All right, so yesterday we just introduced matrices. Okay. At this point, there is nothing really heavy duty going on here, just basic linear algebra. And I think towards the end, I kind of showed why using matrices can be handy in solving systems of linear equations. Okay, so if you write a system like this, a11x1 plus a12, just for a simple case, x2 equal to b1, and a21x1 plus a22x2 equal to b2. Okay. And I showed you the 3 possible cases of systems of linear equations yesterday. So yeah, I can do that at the end of the lecture. Okay, so these are 2 straight lines. Either they may intersect at one point or intersect nowhere, or they could just be on top of each other. Okay, so those are the 3 situations, but more importantly, this could be written as a matrix equivalent form. Okay. So this idea is the main theme of chapter 4. Okay, solving systems of linear equations using matrix algebra, so to speak. And so b1, b2. Once again, if you forgot our notations yesterday, it's a 2x2 matrix here. This is a 2x1. People also call it as a 2x1 vector because it's representing a point x1, x2 in the xy plane. Okay. And this is again a 2x1 vector. And all these numbers are given to you. x1, x2 is the set of variables that you're trying to find. But all of you probably have done this or seen this. Okay, so if you have 2 equations, x plus y equal to 3 and 2x plus 3y equal to 7. I think I am thinking about the right numbers, hopefully. Okay. I think x equal to 1, y equal to 2 is a solution, I hope. Okay. No, 8. All right, so if you're given this system, you don't need any heavy artillery to do this. Okay. But most of you have seen this trick of multiplying the first equation by 2 and then keeping the second equation as such. All these are things you do in your lower middle school or high school or somewhere. Okay. So multiply the first equation by 2 and then you can subtract these 2 and you get y equal to 2. Those kinds of manipulations are easy to do if you have just 2 equations and 2 variables. Okay. You won't go crazy with what's going on. But the idea here is to eliminate one variable. That's the whole point. Okay. No matter how many variables you have, you eliminate everything else and keep just one variable. Okay. Even if you had, say, 700 variables, eliminate 699, keep 1. That's the main theme of linear algebra when you do these problems. Okay. So to eliminate as many variables as possible, in a larger system, okay, this is a 2x2 system, so nobody really cares about how you do it because you could do it by hand. In a larger system of equations, so even if you had, say, 4 equations and 4 variables, that is pretty large enough to do it by hand, okay, unless there are some zeros already waiting for you there. If it is a random set of equations, 4 equations and 4 variables, it's not easy to do it. So the point there is to then eliminate 3 of them and keep 1. Okay. The matrix notation is more convenient than dealing with the equations as such. Makes our manipulations easier because you're just dealing with numbers in certain positions, okay, instead of dealing with equations as such, so you won't go crazy when you're doing it. And that's exactly what MATLAB is trying to do as well. You put those numbers there, try to do some manipulations. So one special form of this matrix, okay, is called the row echelon form of a matrix. So it's abbreviated as REF throughout this course. The word echelon stands for staircase. I think it's a French word that says it's some kind of a staircase kind of a pattern. Okay. All right. So a matrix A, okay, of size m by n, and that is m rows and n columns, is in the row echelon form, or REF, if the following conditions are true. So please write this carefully because it's going to be the main part of chapter 4. Okay. If 1, the first non-zero entry of each row is a 1. Why is 1 so special? It's easy to scale 1 with any number you want. Okay, so 1 is a particularly interesting number other than 0 because of computational reasons. Okay. This first non-zero entry is what you call as the leading entry for that row. Okay. It's also called a pivot element in some textbooks. So all these things are interchangeable. Okay. So it has got some importance there. We're going to make use of that 1 to kind of use it as some kind of a pivot to manipulate all our other calculations. Condition number 2, the leading one of any subsequent row which means any row which is coming after it. Okay. Must be to the right of the leading one above it. That is what is forming the staircase pattern in this case. Okay. So if there is a leading one in any subsequent row, that doesn't have to be, okay, but if there is one, it has to be kind of shifted to the right at least by one position. It can't be directly underneath. Okay. So this is a must be. And condition number 3 is that if there is any row that is full of zeros, that must be at the bottom of the matrix. Okay. Again, it's not necessary that the matrix must have a row full of zeros, but if there is any such row, okay, so any row full of zeros must be at the bottom of the matrix, or it must be the last row or rows. Okay. So that is when a matrix is defined to be in ordinary row echelon form. Okay. So examples. One, negative 3, 5, 7, 2, 0, 1, 2, 3, 5, 0, 0, 1, 2, 3. Good. So the first non-zero entry of this row is a 1. The first non-zero entry of this row is a 1, and the first non-zero entry of this row is a 1. And each one is kind of shifted to the right. Okay. It doesn't have to be exactly in this nice, beautiful pattern. Okay. It could be shifted by more than one column, but at least one column. This is what is meant by an echelon. So this is also row echelon form. 1, negative 3, 5, 7, 2, 0, 0, 0, 1, 2, 0, 0, 0, 1. Okay. This is also okay. Doesn't have to be right next to it, okay, but it must be to the right somewhere. So this is a leading one here. That's a leading one here. That's a leading one of the last row. This is also an REF. Okay. So there is no restriction about how beautiful it should look. Okay, it could be something like this, or something pretty stretched out like this. That's okay. So all these are in REF. Why are these so special? Because all those zeros are giving you the possible scenario of an equation reduced to just one variable. Okay, this is 0x1 plus 0x2 plus 0x3 plus 0x4 plus 1x5. So all those zeros are special because you have eliminated all those variables in the equation. Okay. So let me give you a few matrices, and you should tell me if these are an REF or not. And if the answer is no, you should tell me why not. So are the following in REF? What do you think? Is it an REF? It should be a yes or no. There is nothing in between. We can't say, oh, it's maybe or. What do you think? No. Why not? it's not, this is not shifted, it's not a echelon pattern, right? So this one is violating the second requirement. Okay, so this must be shifted at least to one position here. Okay, so this is not an REF. Good. What about this one? I don't know why I keep writing -3 as the second number always. 5, 9. What about that one? People online, any opinions? People in class think it is an REF. What about why not? I think I probably made it a little tricky there. Why not? I mean, I see a couple of no's. So what is the condition that is violated here? Well, again, that is not a requirement. So I think, the statements for the REF must be very clear. Okay. The requirement in the second one was that the subsequent ones, if there are any, okay. So I mean, if that was not written in a very legally tight fashion, so the requirement is the leading one, if any. Okay. It doesn't have to be there. It's just like the maximum minimum for your calculus functions, it doesn't have to be there, right? So the leading one, if any, for subsequent rows must be to the right of what is above it. Okay. Right of the leading one above it. If there is none, that's not your fault, and that's okay. That's the leading one here. That's a row full of zeros, row full of zeros. That's okay. Okay, so just to be clear that all the rows full of zeros are at the bottom, and the first non-zero entry of any row is 1. Okay, is it clear? So the second one is not a requirement that there should be leading ones in all the rows. Okay, so this if any should be kind of a flexible condition there. All right, what about this one? Let me ask people online, what do you think about this matrix? Is this okay? Why not? The first one is, so these are in the wrong position. Okay, if you are looking at where the leading ones are, this is going the wrong way. Okay, it must be, this must be here preferably. So again, these are in the wrong positions. This is in the wrong position actually. So not REF. Okay. So I hope this is clear. What qualifies a matrix to be in the row echelon form, what does not. Okay. The good news is if something is not an REF, we can always do some manipulations and make it REF. Okay. So all hope is not gone just because they are in the wrong positions. It's easy to convert one to the other by doing some simple manipulations. All right, before I start doing that, do you have any questions about what an REF means? This is the central idea of chapter 4. So let's make sure all of you are okay. Okay. It's time to practice some adding and subtracting numbers. Okay. So if a matrix is not an REF, which means that something is not right and they're in the wrong position, or the ones are kind of offset by some columns or rows which are not supposed to be there. So if a matrix is not in REF, we can do the following elementary row operations. ERO, just to abbreviate it for future lectures. Okay. Emphasis is on the word row here. We are not doing any kind of column operations here. Okay. All operations are done on rows because they are the ones representing the equations in this case. The following elementary row operations. Operation number one, you could add or subtract. Again, subtraction is just an inverse of addition, so there is no need to write it as a separate operation. Okay. Add or subtract any row to a scalar multiple, a non-zero scalar multiple. Okay. Even if that is obvious, sometimes some students think you could multiply something by 0 to a non-zero scalar multiple of another row. Again, all these things are done just to get zeros and ones in the right position. Okay. Operation number two, you can multiply any row by a non-zero scalar. Why is that okay? Because you're taking an equation, say 2x plus 3y equal to 5. Remember that represents a row in the matrix. And nobody is stopping you from multiplying this equation throughout by 2, for example. 4x plus 6y equal to 10. Okay. That is what is going on here. Multiply any row by a non-zero scalar means you're multiplying the equation throughout by that. The third one is probably the most underused operation. Swap any two rows. Okay. Again, we don't do this just for fun purpose. Okay. We do this to make sure that the matrix comes out okay in the REF form. So just don't do random things and make your life more miserable. Okay. And the reason for number 3 to be true is because if you're given two equations like this, x plus y equal to 3 and 3x plus 5y equal to 7, nobody is stopping you from writing this first and that second. Okay. This is the same as writing 3x plus 5y equal to 7 and x plus y equal to 3. Whether you call this as equation 1 or that is equation 1, okay, there's no difference, and that is why swapping any two rows is okay. You should not swap any two columns. That changes the problem. Okay, please don't do it. So all these statements, I think the word row must be emphasized. You should not do any manipulations to columns because that will change the variables and the equations. Okay. All right, so I think I'll start doing examples on Monday. Okay, I think I don't want to rush through this. So let's kind of slow down, and we have 5 minutes to 8:30. Let me go through this example that one of you asked here. Okay, so we will start doing examples for REF on Monday, so you can have a relaxing weekend. Okay, not much homework to do this time. All right, so let me just look at this question here. So this is section 2.42b. Okay. Somebody will have to read the question out for me. I forgot, or I don't remember actually. 3.42b. If you could unmute and read the question out, or you could type it in, I don't know which one is easier. Or if you have a textbook here, I don't know.
I'm pretty sure it's y prime plus 2y.
Might find it take some time for me to pull this out. So 1 second.
I can read it to you if it's easier.
Oh, sorry. Did you say that?
Yeah. It's y prime plus 2y
Uh-huh.
equal to u sub 5 of t,
Uh-huh.
and then y sub 0 is 1.
Okay. That's a first order equation, right? So I hope all of you, though I don't use that notation on my quizzes and tests, okay, this is the same as saying u of t minus 5. Just the Heaviside function, which is delayed by 5. Okay, so that is the meaning of that notation. It's a first order equation. That is why there is only one condition given here. So take the Laplace transform on both sides. You have Ly prime plus 2 L of y equal to the Laplace of u of t minus 5. So now you can make yourself a Laplace table, which should be right next to you when you write the test. Okay, s times y of s minus y of 0, which is not equal to 0 here. So please just make sure that the term is written here, plus 2y of s equal to e to the power of negative 5 s over s. Okay. And y of 0 is 1. So you have s plus 2 y of s minus 1 equal to e to the power of negative 5 s over s. Okay. Just sorry if my 5 and s look the same for both. So that's a 5, that's an s. Add 1 to both sides. So we have s plus 2 times y of s equal to e to the power of negative 5 s over s plus 1. Okay. And divide both sides by s plus 2, which I could do it right there. Okay, so that's where the first part of the problem ends. So you solve algebraically for y of s. Okay, up to here, all the problems are easy, right? You copy from the table, push the terms left and right, and you get that part. Now this term is already done. Okay, the Laplace inverse of this is e to the power of negative 2t. There is nothing to wait for in that particular term. Okay, it's only this part that you need to do some work for. So that second term came from the initial value. Okay, so there is no need to shift it. So that's done. So okay, so let's take care of the first part, which requires partial fraction. This shouldn't be here. So we have 1 over s times s plus 2. Okay. Again, you don't have to keep the e to the power of negative 5s when you do the partial fraction for this term. Okay. So that is a over forgot, is it bs plus c over s plus 2 or b over s plus 2? Okay. After I started linear algebra, I started forgetting all these things. So you have to help me. Okay. So clear the fraction, have 1 equal to 8 times s plus 2. So s equal to 0 will give you a equal to half. Yeah. and s equal to -2 will give you b equal to negative. So that y of s that we had up there that's going to be, yeah, let's see, e to the power of -5s times 1/2 over s minus 1/2 over s plus 2. And you also had that second term which was not shifted. Okay. So you could either write the s term or the Laplace, the function itself, that's up to you, because there is nothing to do there. So you just have to, if you want to keep things uniform, you could just write it in terms of s. Sorry to dance back and forth. That way everything is in terms of s. You can just invert it term by term. Okay. So y of t. This one includes a second shifting theorem backwards. So what happens to that term now? U of t minus 5. Okay. The answer should be in terms of t because I have no idea what s is, right? The function was given in terms of t, answer should be in terms of t. Okay. Times 1/2, that's a constant, case 1, minus 1/2. What do you write in that term? Maybe somebody online can help me out here. What happens in that term there?
Should it be
Mhm.
e to the -2 parentheses t minus 5?
Good. Plus e to the -2 t minus 5? No, okay, just e to the -2t here. Because this term was there from the beginning, okay, so that just sweeps through and comes back here. So this mechanics is the same, even if the second order, you probably have one more additional term probably, okay, but the process remains the same. One humble suggestion, please copy the problem correctly. Don't make a monster out of things which are easy, okay. Especially if you have the delta function on the right hand side, please make sure that you don't make it worse, okay. So that'll be my only advice to you, but otherwise it should be a pretty straightforward test. Okay. Yeah, I think there were a couple of typos on the answer key. Maybe this was one of the examples where the shifting was forgotten, okay, which I should change at some point. All right, any other questions before I wind up? I can stop recording and then if people want to ask outside of the recording, I could wait. All right, so don't forget to write the test today. Okay. And,